All right, gang, Math 5500. Going to be a lot going on in this video, and I've been trying to keep my videos at 20 minutes because research shows that that's the most effective, well, 20 minutes or less. Well, I don't know. I don't think a video of 2 seconds would be very, but anyway, around 20 minutes. So I'll try to keep it at that, and if I'd quit talking about useless stuff, maybe we would get that done. All right, I don't know why I am all of a sudden writing like up. Uh, I told you, I think previously that studies have been done that shows that that's just evidence of extreme confidence or something, which, whatever. Uh, okay, anyway, what we're going to get accomplished, hopefully, in this video, if I'd quit talking and get on task, we're going to use the dataset ACT district, so if you want to go ahead and locate that in the dataset folder in Blackboard. We're going to look at dummy variables, t-test for estimates, and the f-test for the regression relation. And I'm going to do it in this order. This is going to be first, this second, and this third. All right, so, but the primary focus here, I think, is review, and then teach new stuff in terms of the dummy variable. Now, what I want you to know on let's say, for example, that we are predicting first year college GPA from, of course, a beta 0, and let's say, a beta 1, which is, the coefficient for maybe ACT, and a beta 2, which is a coefficient for high school GPA, whatever. Just a few predictors here. From the coefficient estimate perspective of the t-test, what we conduct is we conduct multiple t-tests. So the first thing I would conduct is the beta 0 equal to 0 versus h sub a beta 0 not equal to 0. Now, if you've been paying attention, you know that I don't find this testing the significance of the intercept to be that interesting. But nevertheless, it is tested in the R output. The other thing in this situation, we would test that the slope of ACT is not equal to 0. And similarly for the high school GPA. So the t-test for the estimates of the regression coefficients conducts 3 separate t-tests. And we see them on the line. We see the estimate, then we see the standard error, then we see the test statistic, and then we see the p-value. All of this is created from its own test statistic, which will be the estimate minus the hypothesized value over the standard error for the estimate. And I'm not going to run through each of these because it's pretty self-explanatory, at least from the background that we have now. The estimate is just the coefficient that we get from the R output. That's just multiple ways to find that, and then the standard error for that particular coefficient would be found using the variance-covariance structure for B, which we've studied pretty much ad nauseum. Now, let's move into Anova. All right, so what's really going on in Anova in the context of this example? Well, here we have the assumption that both of our predictors, the slopes, are equal to 0. So we're not looking at it in terms of a coefficient diagnostic or coefficient test. We're looking at it in terms of a model diagnostic. Are both of these things equal to 0? Our H sub A would be that either or both are not equal to 0. So again, the Anova is a model diagnostic. It assesses the fit of the model, not separately through the t-test. Now, what's the Anova, and I'm just kind of setting up the stage here, what does the Anova table look like once we introduce multiple predictors? Well, in the classic case, we still have our source, which is still going to be the regression, the error, and the total. We still have our sum of squares, which is easy to find. For example, we've seen previously that the sum of squares for the error is y transpose y minus beta transpose x transpose y. Okay, and we've seen that the sum of squares for the regression, the sum of squares for the total is just y transpose y minus 1 over n y transpose jy. And of course we've seen the regression as well. So now we get into the degrees of freedom. The degrees of freedom turn out to be if we let k equal the number of predictors. Now, I think this is the easiest way to remember the degrees of freedom for the Anova table. Now, not including beta 0. Beta 0 is not really a predictor. Our degrees of freedom for the regression term just turns out to be k, the number of predictors. The error term turns out to be n minus k minus 1, and the total just turns out to be, as it was before, n minus 1. So you can see that when we add the degrees of freedom for the regression and the error terms, we get n minus k minus 1 plus k, which gives us n minus 1. Then the mean square development is exactly the same. It's the sum of squares regression divided by k, and the error term, of course, is the sum of squares error divided by n minus k minus 1. Typically don't look at the mean square for the total because these aren't additive. Then we get our f statistic, which of course is the ratio of these two values, and we can calculate our p-value accordingly. So what we're actually looking at here is we're looking at the f distribution with degrees of freedom k, n minus k minus 1. Now, in a simple linear regression case, how many predictors do we have? Well, we have 1, and that's why we put a 1 for the degrees of freedom of the regression. So, all this stuff has been covered previously. I just wanted to wrap up a few things. Sometimes when I finish a video, it'll hit me. I wish I'd gone into a little bit more depth on a couple of things, and sometimes I'll just scrap the video and create a new one, and then sometimes in the next video, because guys, you expect to come to class every day, all right? So, and that the equivalent of coming to class every day is watching the instructional videos. I think that about nails what I wanted to do here. So let's dive into. I feel like I'm forgetting something, but I just don't know what it would be. Okay, well let's escape this and get out and go to the illustration of dummy variables. Now, one thing I do want to, let me bring this back. All right, for dummy variables, and please forgive me for the simple nature, simple level for this illustration, but when I'm teaching like y equals mx plus b to my maybe my intro developmental math courses, or maybe an Algebra 1 class, whatever. It's been forever since I've taught anything at that level. What I do to try to motivate the interpretation of the m and the b, which we all know is the slope and intercept respectively, is I give one of these one of these very meaningful tables. And I say, well, what would the table look for? Y equals 3x plus 7. Well, we put 0 in there, we get 7, and we get 10, and then we put and get 13. All right. Then, in trying to motivate the idea of what a slope means and what an intercept means, I say, okay, let's look at this over here. Every time we increase 1 unit, we typically we increase our y 3 units, don't we? Do you think it's by accident that these two numbers turn out to be the same number? No, it's not by accident, because it is precisely the definition of the slope. As x increases 1 unit, the change in y is 3 units. That's what our slope is. That's the definition. Then I asked them, do you think it's by coincidence or by design that 7 just happens to be beside of x equals 0? No, it's because by design. That's precisely what the intercept is. It's the value of y when x is equal to 0. Now, transition that into b0 plus b1x, right? You think that helps us define our intercept and our slope? Well, absolutely it does. The intercept is the predicted y, so we're no longer looking at y's, we're looking at predicted y's. Of course, predicted y's aren't observed, so that's kind of confusing. But in the spirit of our regression model, the interpretation of our beta 0 is the predicted y when x is equal to 0. The interpretation of our b1, our slope, is as x increases 1 unit, our predicted y increases b1, b3 in this case, right? Well, that leads us into dummy variables. So if I am predicting, say a GPA from GRE, where GRE is quantitative, and I have a slope of maybe 0.15 for GRE. So I have my predicted as whatever my beta 0 is plus 0.15 times GRE. The interpretation of that is what? Well, as we increase GRE by 1 unit, the predicted GPA increases by 0.15 units. All right? So that's pretty easy to do. Now let's say that we're predicting GPA All right, so stay with me, guys. Now we're predicting GPA from gender. And again, I wouldn't do this. This is just for illustration purposes. If I was looking at going to examine the relationship between gender and GPA, I'd run probably an unpooled 2-sample t-test, right? I wouldn't use a single predictor that's categorical dichotomous in this case. But just for the sake of the illustration, let's say we did that. And we could, right? So here, again, I've got my predicted value, I've got my beta 0, I've got my coefficient, and I have gender. So could I interpret this? Well, what does a 1 unit increase mean? Well, 1 unit increase means we're comparing females to males, right? We're increasing 1 unit. So whatever this is, this tells us that whoever's coded 1 scores 1.2 higher than whoever's coded 0. A 1 unit increase can even be interpreted when we have categorical data as long as it is dichotomous. But What if we're trying to predict GPA from school district and we have 5 school districts, A, B, C, D, E, for example? What's a 1-unit increase mean? Well, we don't know, right? A 1-unit increase isn't anything. We can't make these things zeros, 1, 2, 3, 4, and so on, or 1, 2, 3, 4, 5, whatever, because those are just placeholders. They don't take on a quantitative meaning. We're just using a number as a placeholder, as an assignment of a category. So because increasing 1 unit in the coefficient has absolutely no inherent meaning, at least no meaningful interpretation when we deal with categorical data. Now, because of that, what we have to do is we have to create dummy variables. So let K equal the number of levels. We're going to choose a base group. Of zeros and ones. Zeros not in that group, 1 is in that group. So I think I gave an illustration of the new matrix, so to speak, of zeros and ones in a previous lecture. So I'm going to go directly to the application of that.